Alright, we're back. Sorry about that. Let me just wind down the music here. Welcome back to Chem 140. It is Monday, week 7. There is not really that much left in the quarter. I mean, there's a lot of content for us to cover, but in terms of time, the end is coming up pretty quickly. We're going to be getting back into math pretty soon. We have, I think, 2 units left of just conceptual stuff. And then we're going to hit the math hard until we get to the end of the quarter. So, today is Unit 10. We're going to be drawing Lewis structures today. Things that are due on the agenda. There is a lab worksheet. Worksheet number 3 is due tomorrow, the 18th of May. That's a soft deadline. Make sure you get it in by then. If you need an extra day, it will close on the 19th. So keep that in mind as you plan ahead for your work week. Unit 10 is real short. We're probably going to finish this in the first hour, maybe in the first hour and a half. And then we'll start Unit 11 today, which is naming. So let's get started. Okay. So all of Unit 9, we have been talking about... Oh, I had to yawn. Hold on. Excuse me. All of Unit 9, we were talking about ionic bonding. Ionic bonds, how they form, sharing electrons, things like that. Unit 10, we're going to talk about covalent compounds and how they are drawn in terms of their structure. Now, how do we know that covalent compounds must be unique from ionic compounds? And the answer is, well, if we look at their properties, the properties that they have don't really match up with those of ionic compounds at all. So, for example, water is a liquid at room temperature, but no ionic compound is a liquid at room temperature. Gasoline is a liquid at room temperature, but no ionic compound is a liquid at room temperature. And there are numerous compounds that are all liquids at room temperature. If you want to make a liquid out of something like, say, sodium chloride, you have to heat it to like 890 Celsius. Like, it's insane how high you had to heat that temperature. But these other things are liquids all around us. There are also other things that are solid, but they tend to feel like semi-solid. So like candle wax. Candle wax is very like squishy. You can manipulate it, even with just a little bit of heating or even when it's just cold. If you have stuff like sugar, powdered sugar, if you look at that really, really closely, does not look like salt crystals at all. Powdered sugar just looks like kind of fragmented stuff. And for a long time, people thought, well, there must be reasons for these explanations. There must be reasons for these differences in properties. And it turns out that it has entirely to do with their bonding. So what we're going to study in this chapter is a little bit about the bonding in covalent compounds and how we form them. Because it must be unique. It has to be totally different. Otherwise, the properties would be identical, right? Now, it turns out that when we do the analysis of atoms within covalent compounds, the end goal is more or less the same. Atoms want to attain an octet. The issue that arises here is that if I take two atoms that are nonmetals and I ask them to transfer electrons, I end up with a dilemma. For example, we're going to put fluorine on the screen here, and then I'm going to put chlorine on the screen here. Fluorine and chlorine are both nonmetals. They both have 7 valence electrons because they're in group 17, right? How do I transfer electrons from one to the other so that both get an octet? Well, if I do this, then this is good, but this is further away from its octet, right? It's trying to get to 8, now it only has 6. Likewise, I can't do the same thing where I just pass the other one back because then the chlorine on the right would only have 6. So transferring electrons is out. That's no good. If I transfer electrons and both are just really close to reaching their octet, the one giving the electrons away will always end up further away from the octet, and that's not good. That is not the goal here. So we need another approach. We need to do something different. And what ends up happening is that instead of transferring electrons, electrons get shared instead. And this is where the word covalent comes from. Co meaning communal, and then valent meaning valence electrons. So in other words, any electrons that are shared for a bond are going to be put in a community sort of area. In other words, between the two atoms. And if I put those electrons in the community area, then both atoms get to count them for their octet. Now, visually, that's going to look like this. I'm going to take 2 fluorine atoms, and I'm going to put them on the board here. And what we're going to do is, instead of transferring electrons, we're going to share the unpaired electrons. So I'm going to share this electron, and I'm going to share this electron in the following way. And so now they're in the community area. And of course my eraser broke. Hold on. So now what ends up happening is that because my electrons are in the community area, I can do the following. Does my atom have an octet? Well, I've circled 8 electrons. How about this other one? Does this atom have an octet? It does. I have circled 8 electrons. But you'll notice that I have double counted the shared electrons. And those shared electrons are what make up the covalent bond. So in other words, what are atoms doing to get to an octet? Well, they cheat. They need to get 8 valence electrons. That's not possible by transferring. Let's just double count them. Nobody's going to know, right? Don't worry, nobody's going to know. Huh? So there you go. Everyone has an octet. Everyone is happy with this arrangement. And then this is just talking about what a covalent bond is. So atoms don't have brains. They don't care that they don't actually have 8 electrons. This is a stable arrangement of charges because the shared electrons are placed between 2 nuclei. And so the electrons are attracted to both nuclei, and the electrons are otherwise just kind of stuck there in the middle between the 2 fluorine nucleus. Oh, sorry, I'm trying to talk around yawning here. Now, we don't really draw all of these dots in the middle as shared because putting a lot of dots there gets cumbersome. So what we do is we replace shared electrons with a line. Anytime you see a line, that is the equivalent of 2 shared electrons. That's these right here. Now, if we drew 2 lines because we shared 2 pairs of electrons, that would be like putting 4 electrons in there. And so on and so forth. You can put as many lines as you want. Each line represents 2 electrons. For our purposes, we're never going to see more than 3 in this class, and we'll see why that you can't actually get a 4 in a second. But it is possible to share more than 3 pairs of electrons if you involve metals. What? That was my degree. You can get some really crazy shit with transition metals and covalent compounds, especially if the metals have like moderate electronegativity. That's a word that we haven't used in this class yet, so we'll come back to that 161. There is a whole gray area for all of this stuff that I'm teaching you, and it's beautiful. All the crazy fun things that you can do. And there's still more out there to be discovered. So for our purposes, each line is going to constitute 2 dots. I'm going to get rid of this because that looks like a double bond. So a single bond is 2 dots. A double bond would be 4 dots, and so on and so forth. On the outside here, I have the little pairs of electrons that are not participating in bonding. We're going to just call those non-bonding pairs. When you draw your structure, you do want to draw the non-bonding pairs. This will be very important in 161 and then organic chemistry. Knowing the positions of your non-bonding pairs helps you dictate the shape and geometry of your molecule. And it turns out that in biology and inorganic chemistry, organic chemistry, anything that where you're going to be synthesizing materials and stuff that are reasonably complex, shape is everything. Molecules fit into enzymes based on their shape, and if they don't fit in the enzyme, you can't do the reaction. And if you put the wrong molecule in there because it has the same shape, that could kill you. That would be poisonous. So, shape is going to matter, so please do draw all of the dots so that we can illustrate the shape later on in 161 when we get there. Now, when you do covalent bonding with molecules, some things that you want to remember are the following. Every time you draw a line between 2 atoms, the line will count as 2 electrons for each atom it connects. So that's both sides. When we draw lines, I'm going to just designate this as A here. And this will be B. You only hook between unpaired electrons. So this connection is going to be where the bond is formed between these 2 unpaired electrons that I've shown. The non-bonding pairs that you filled in from the Lewis structure of just the element by itself, those remain and hang out. They never get to bond because they're already paired. They have already done their part to get to 8. Now we need to make bonds to fill in the rest of the spots. So this would then become A with these guys unpaired still. Line B, and those would remain paired. Okay? We are only connecting unpaired electrons. So in other words, really what we're doing is we're just playing connect the dots, right? That's Lewis structures at its most basic level, is connect the dots. When you are finished with your structure, the total number of electrons around every atom should be 8, including the bonds. So if I circle a position like this, right here, I would say, okay, this has an octet because it is 1, 2, 3, 4, 5, 6 lone electron pairs here. And then it has 1, 2 electrons in this bond. But if I circled this A, I would only get 5 electrons. 2 from the bond and then 3 from the unpaireds. I would need to find another 3 electrons by making 3 more bonds to 3 other things. Then it would have an octet. Now, there are always exceptions because, of course there are, right? The exception is hydrogen. Hydrogen only cares about 2 electrons. Instead of getting an octet, hydrogen will settle for 2. And the reason for that is hydrogen is tiny. 2 electrons is enough for him. He's just happy with 1 more. All right, so whenever you see hydrogen, just make sure that you connect one thing to its dot. Don't try and make 74 bonds to hydrogen. Just connect its dot to any other unpaired electron to form a bond, and your hydrogen will always be happy. All right, so what I want you to do... I guess we're not doing that. Just hold on. Sorry, I thought it was... Yeah, there we go. Okay. I thought we were going over the examples right away and then talking about multiple bonds. Sorry, I'm just drinking some water. Excuse me. Now, we've already implied that you can maybe make multiple bonds. Of course you can, right? In some cases, you will need to make more than one bond to the same atom to give everybody an octet. So, for instance, here's oxygen. Excuse me. How do I get both oxygen atoms to have an octet here? And the answer is, well, if I share these electrons together, that pairs them together. And if I share these electrons together, that would pair those together. Each atom, which starts with 6, would be gaining 2 electrons from the other one that are shared. And the end result would look like this. And now when I do my octet, I go like this. Well, I still have 8 electrons. And I still have 8 electrons. I didn't mean to pierce through them right there. But those do count. Again, when I draw 4 electrons in a bond like that, we represent it with 2 lines. Each line represents 2 electrons. There are 4 total electrons in a double bond. And we've satisfied the octet rule for both atoms. Now, in theory, you could do this with nitrogen as well and observe a triple bond. So nitrogen looks like this. It has 5 valence electrons because it's in group 15. How do I make this work? I can share this electron, and I can share this electron, and I can share this electron. And the end result that we get looks like this. And this would be my triple bond, which has 6 electrons shared in it. And 3 is going to be our theoretical limit. And the reason for that is because with carbon, if I try to do this with like that, I could share these, I could share these, I could share these. But this one, bonk, oop, I hit the nucleus. I can't share like this because charges go in straight lines. So I can't get these too close to each other. That's just not possible. But for the other ones, I totally can draw a straight line, uninterrupted, to the other electron. So at best, what I can do is I can do something like this for carbon, and then I have to make another bond to something else that has an extra electron. So you're never going to draw more than 3 bonds between any 2 atoms in this class. 161, we're also going to stick to that rule. And in OChem, you're also going to stick to that rule. It's not until you get to like 300 level chemistry, if you can go that far, that you'll be making more than 3 bonds, and only in very, very, very rare circumstances. But it's really cool. You totally can do it. All right. So we already did the Lewis structure for nitrogen on the previous page. If you grab your periodic table, and I'm going to replace these numbers here with the numbers that are actually on P table that we've been using here. Hold on. That's not dark enough. We'll do this. All right. So if I'm using P table, the number of bonds that form around an atom is usually conforming to this pattern. For example, if I have chlorine, chlorine is in group 17. I'm going to make one bond. If I have oxygen, I'm going to make two bonds. And that might be the same atom or not. Something like phosphorus, which is in group 15, can make three bonds. And something in group 14 can make four. How does ozone bond? We're going to talk about ozone. We're definitely going to talk about it in 161. It might come up when we get to the next section of chapter 10, which is how to make a Lewis structure for anything. We can totally do that, because you'll notice that there are some weird things that come up in some cases for molecules as they get more complex. So this connect the dots and how many bonds thing is just a guideline. It's not always correct, but it is a guideline. And molecules like ozone break the guideline. All right, so for most molecules, you will observe that elements will form a number of bonds based on their group number. This is not always true, though. So again, remember, this is a guideline. And that it is possible to violate this in various forms. Now, for the molecules that I'm going to give you on here, all of these molecules follow the guide. These are very simple molecules. You can solve these by playing connect the dots. The last one's a little tricky. There is one correct answer, though. Remember, you can't have any unpaired electrons hanging out. You got to bond all the unpaired electrons. The paired ones that become non-bonding, they just sit there. Leave them be. Okay? But what I want you to do is draw out all the Lewis symbols first. So, for example, for Cl2, draw the correct Lewis symbol based on the number of valence electrons it should have. And then try and figure out a way to connect the dots. And then draw the correct Lewis structure. Do that for all 6 of these, and we'll go over the answers in about 5 minutes. Okay? Good luck. We're all counting on you. See you in a bit. 1 or 2 more minutes, we'll go over the answers. All right, let's go over the answers here. I should be able to do these all on this page, so. All right, so we're going to look at Cl2. I'm putting in the dots a little bit too quickly here. I should be doing it the correct way, really, so that you guys don't copy me and just memorize these. So there's my chlorine. 1, 2, 3, 4. I'm going to leave one of them unpaired. I'm going to pair these two, and then that would be the structure. For BRF, you're going to notice that, well, wait a second, I get exactly the same thing. And yeah, you totally do. Foop, there you go. And that makes sense because they're all elements that are in group 17, right? So they all have one unpaired electron on them, so the only option is to just pair those. Now with carbon and fluorine here, I'm going to draw this like this real quick. Oh, I ran out of space down there. That's okay. And so the obvious thing to do is if I'm going to hook them all together, I would just connect, okay, do, 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 do. But remember, bonds need to go in straight lines, right? So this sort of structure is Garbo. This is like a football diagram, but it can help you. So now what we have to do is tidy up. So we will tidy up. And then I will get a structure that looks like the correct structure, which would be this. And once you get to this point, you can just put the dots in. And there you go. So that's the structure for CF4. All right, you pause the video if you need me. If you need to write that down, I got to hit clear because I ran out of space. There it goes. So for water, here's my hydrogen. Here's my hydrogen. Here's my oxygen. We're going to go boop, boop. And then we'll tidy up. And there you go. There's the structure. Now, if your H's are in a straight line, HOH sort of thing, that's fine. All we care about is the connections are the same. So my H connects to an O, connects to an H. However you orient it, it's fine. We got OF2, so we'll do oxygen. So there's my oxygen. And I did it really quickly again. I got to do it the right way. There we go. We're going to do that to this unpaired and that to this unpaired. Then we'll tidy up. There you go. Simple enough. I'm going to hit clear again. So pause the video if you need to copy it. And it's gone. This next one is a little bit trickier to try and determine what you want to do with this. How the heck do I connect all these pieces? Well, first I should connect the C's. Boop. So we got that. And then I have a bunch of places I can put H's. Well, the only thing that I can really do to make sure that I connect every electron is that I put 2 H's on each side here like this, and then do that and then that. And then now I can pair these together. And that looks really stupid, so we're really going to tidy this up. And that's what our molecule looks like, which you might have rotated. Now, if you put 3 of the hydrogens on one side, for example, if you did something like this, what you inevitably end up with is, well, I got to put 1 H somewhere, and then I have this. You cannot pair these two. You have to pair them with other atoms, because this would not have an octet, right? Over here, I would only have 2, 4, 5, 6 electrons. That does not make an octet. So this structure would not work. Okay, so there are some ways that connect the dots lead you kind of down a rabbit hole. And if you have too many options with like carbons involved, it sort of becomes a guessing game. So for very simple molecules, this connect the dots strategy works out pretty well. But as we increase the complexity even slightly, it all falls apart. And so what we need to do is we need to devise a method that will get us the right Lewis structure every single time. And so that's what we're going to do with this next bit. So if you have molecules that have double bonds or triple bonds in them, or they have a bunch of carbons, everything starts to fall apart. And these rules get more and more difficult to just assume. But if we follow these rules that I'm about to establish here, this is what I call the 5-step plan, then you get the same result every time in a consistent manner for larger and larger molecules. So what is the 5-step plan? The 5-step plan involves figuring out how many electrons you're going to play with for bonding, then creating some sort of framework, and then just painting in all the electrons around the outsides, and then filling in the inside as needed. So let's do that. Let's go over all the rules first, and then we're going to apply them to a molecule. So in our 5-step plan for figuring out the Lewis structure of something, the first step is going to be counting valence electrons in all atoms. Now, how do you count valence electrons in any atom? So if I had a carbon, this is group 4 or 14, so it would have 4 valence electrons. What about oxygen? Well, oxygen's in group 16, so it has 6 valence electrons. So if I had instead carbon monoxide, that would just be 4 plus 6, or 10. And so these are, again, valence electrons. You could count the number of valence electrons for any molecule you want to. If it's H2O, add the number of valence electrons that each H gives you and each O, and sum them all together. You get 6 plus 1 plus 1, which is 8. And so on and so forth. Step 2, once you've counted all your electrons, is you're going to create what's called a framework. Some textbooks call it a skeleton. Same thing. You're going to take your atoms and connect them with bonds. Bonds use up electrons, so you're going to deduct them from your total pool that you've calculated from step 1. Now, when you draw stuff based on your formula, remember the formula is trying to give you a hint as to its structure. The first element is usually the central atom. If it's H, then the second element is, because H can never be the central atom. H can only form one bond to something, so therefore it can never be in the center. If you have a bunch of atoms, such as in C2H4, you want to keep the atom that is listed first as central as you can. Which is why we put all the H's around it equally in that previous example. Once you've created your framework, you're going to just fill in all the remaining electrons from your pool. So if you counted X number of electrons and you used up only a few of them, you'll have some that are left over. And so when you go through your Lewis structure, you're going to put electrons on the outside atoms, and then on the inside atoms, until you're out of electrons. I saw your question there. I'll answer that in just a second. So for step 3, we're going to put octets on the outside. And then for step 4, you're going to put octets on the inside. Or on the central atom. So do the outer octets first, and then the central atom octet next. Finally, if you get to a point where you run out of electrons, and you can no longer put electrons on the central atom and not everything has an octet, then you start making multiple bonds. We're going to go over these steps again and again as we do these examples. However, some important things for doing this 5-step plan is you have to do the steps in order. And once you skip a step, for whatever reason, you're not allowed to go back to it. So if you do the steps out of order, I guarantee you'll get the wrong Lewis structure. So be careful. Do step 1, then do step 2. If you are ever at a point where you cannot do a step, you go to the next one and you don't turn back. For instance, maybe you don't have any electrons left over for step 4. You skip it, you go to step 5. Now, if at any point in drawing your Lewis structure, everything gets an octet, or all your hydrogen atoms, all your hydrogens have 2 electrons each, you skip all remaining steps and you just stop. Your Lewis structure is correct. So if you ever get an octet for everything, the Lewis structure is done. This can happen as early as step 2, believe it or not. In some cases, it's just done at that point. Alright, so we have seen the 5 steps. So now what I'm going to do is... That's from the previous class. Let me get rid of that. We don't really need this, so I'm just going to shove it in the corner here. So I'm going to write out the rules again, just so that we have them available for us here. So step 1, count valence electrons. Step 2 is going to be our framework. Step 3 is outer octets. Step 4 is central atom octets. And then step 5 is multiple bonds. There's our super short condensed version. All right, I'm going to give you carbon dioxide. This is going to be our demo molecule here. We're going to do all 5 steps using CO2. Then the slides are going to do it. We'll just skip through those. And then we'll do a few more, and then you can practice with it. Okay. So let's do step 1. Step 1, count the valence electrons. Well, in carbon dioxide, each carbon provides some number of valence electrons. According to the periodic table, carbon is in group 14, so it has 4 valence electrons. Each oxygen provides 6, because it's in group 16, and there are 2 of them. I'll add those numbers together. That's the total I get. So 6 times 2 is 12, plus 4 is 16. I have 16 valence electrons to work with. That's step 1. All right, let's do step 2. I'm going to do the framework. C is listed first. It's the central atom. So I'm going to put the oxygens around it. You can put them wherever you want to. It doesn't matter. Anywhere's good. What you do need to do, though, is connect them. So I'm going to do this. Each line, which is a bond, counts as 2 electrons. So what that means is that for my total right here, I need to subtract out the electrons that I used. And so this is how many electrons are left now, because I used 4 of them for bonding. That was my framework. Everything is now connected together. I have a molecule. I just need to distribute the remaining 12 electrons around the molecule in such a way that everyone gets an octet. So let's do that. So let's do step 3. Step 3 is outer octets. Here I'm just going to ignore all of the do one dot on each side and then do the second for pair. I'm just going to go like this. Do. Octet. How many electrons did that use? I needed 6 electrons to do that. Let's do the same thing over here. Do. Each dot is 1. I use 6 electrons to do that too. All right, let's go pay for my electrons. So I used 6 plus 6 electrons here. And uh-oh, we're out of electrons. There are no more electrons that can be used because we've used all of them for the structure. Now that's a problem because step 4 is make octets on the central atom. My carbon does not have an octet yet, and I have no more electrons to give. So I can't do step 4, so we have to skip it. The last step is make multiple bonds if you have to. Well, in this case, we need to make multiple bonds because I don't have an octet around carbon. It only has 4 electrons around it. Everyone else has 8. They all have octets, so they're good. So here's what we do. We erase a pair of electrons, and we make it a bond of electrons. And if I look at this oxygen right here, I still have an octet because I have 1, 2, 3, 4, and then each bond is 2 each for a total of 4 plus 4 is 8. What about my carbon, though? Well, I have 1, 2, 3 bonds. I probably shouldn't use dots here. So now instead of having 4 valence electrons around it, I have 6. So I'm closer to my octet, but I'm not quite there. So you're probably thinking, oh, okay, well, I'll just make another bond. And the answer is, yeah, you absolutely do that. We'll do it on the other side just to make it symmetrical. I did it in the wrong color. Not that it matters. There we go. So in doing that, now if I check my octets, this oxygen has 8 electrons, 4 dots, and then 2 lines, which are each 2. This oxygen is identical to the other one, and then this carbon has 4 bonds around it for 8 electrons. So this structure that we have drawn here is the correct Lewis structure for CO2, using the 5-step plan. All right. So now that you've seen the 5-step plan in action, I'm going to give you more molecules to try with it, but we are due for a break. So let me just skip ahead here. So if you want to go through these slides and look at this during the break, so I'll leave it on screen for a second here. This is just another approach to how we did this. And then we're going to come back and draw the ammonia structure in a second. Now, to answer your question about carbon monoxide, when you draw the Lewis structure for carbon monoxide, you end up with something like this, which breaks the rules that we said before, where carbon likes to bond to 4 things and oxygen likes to bond to 2 things. Turns out, in this case, carbon can only bond to 1 thing 3 times, and I have a pair of electrons on it, which is weird, and not what you'd expect from drawing its Lewis structure where it's just carbon by itself. Carbon having an electron pair like this usually indicates reactive. And it's that pair of electrons in carbon monoxide that is dangerous. It bonds to your hemoglobin irreversibly, and you basically have to trash that entire molecule. So, see, carbon monoxide will asphyxiate you by plugging up all of the sites where oxygen should go in your blood, and then you die. So, don't breathe carbon monoxide. Always barbecue outdoors. If you learn one thing from this class, barbecue outdoors. Alright, I'm going to set the timer. I'm going to hit the music again. And we'll be back in 10 minutes to go over ammonia, and then I'll have you draw some more, and we'll be done with Unit 10. Okay? See you in a bit. Oops. That's okay. We'll wind this down here. Alright, back to our Lewis structure. So what I want you to do for this exercise, I want you to take NH3 and instead of drawing it using connect the dots, which would work, instead apply the 5-step plan. Do step 1, count all the electrons. Step 2, excuse me. Step 2, draw the framework. There we go. That'll probably be more helpful for you to have the rules on the screen. Step 3, outer octets. Step 4, inner octets. And then step 5, multiple bonds. So what I want you to do is draw the Lewis structure for ammonia, following the rules that we used below. And I'll leave CO2 on the screen, although I'm going to clear it once we get started. So I'll give you about 3 or 4 minutes to do this, and then we'll go over the answers together when we get back. One more minute, we'll go over the answers here. All right. This is what happens when I answer emails from my work email during breaks, is I take way too long. That's not the right button. There we go. Boop. All right, so let me hit that, and then I can get the pen. All right, so we're going to draw the Lewis structure for NH3. So first, let's write its formula. Now we're going to count the valence electrons. So nitrogen gives you 5 because it's in group 15. Each hydrogen being in group 1 gives you 1, and there are 3 of them. So I have 8 electrons to work with. Let me draw my ammonia. I'm just going to put the H's around, oops, that's not what I meant to do, wherever I want to. And then I'm going to connect them all. That uses up 6 electrons for bonds. You don't need to write out what you're doing here for a very strict inventory if you don't want to. I'm just doing it to teach you guys what's going on. So that was step 2. Step 3 is outer octets, but all my hydrogen already have 2 electrons because all they need is 1 bond and they're good. So I skip step 3. Step 4 is central atoms need an octet. Well, my nitrogen doesn't have an octet. I have 2 electrons left. Let's just put them there. I've used all the electrons. I don't need to make multiple bonds because everything has an octet already. My nitrogen's good, so this is the correct Lewis structure for ammonia. Now, again, only connectivity matters. So if you drew your, like, H, I don't know, if you did it like this instead, maybe. Totally fine. Maybe you put this over here. Like, whatever. It doesn't matter. As long as they're all connected in the correct configuration, where you have 3 bonds coming out of your nitrogen and then a pair of dots. You're good. All right, and then huzzah. Oops. Double tapped my keyboard there. All right, I'm going to give you a bunch of these. And I want you to draw the Lewis structure for all of them using the 5-step plan, okay? You're going to notice that some of the molecules will look similar to each other, like CS2 looks a lot like CO2. Why might that be? Has nothing to do with the atoms themselves, but everything to do with where on the periodic table they are. Okay, so draw these Lewis structures. I'll give you 5 or 6 minutes or so to do as many as you can, then we'll go over the answers together. And then we'll move on to Unit 11. All right, one more minute. We'll go over the answers here. All right, so let me first clean up this sheet here. There we go. Boop. Oh, that's not what I wanted. Hold on. There. All right. I'm just trying to set this up so that now when I can draw all over this, and then if I select all and delete it, it just gets rid of that. So there we go. All right, so we're going to do this for all of these molecules. We're going to go through it pretty quickly, though, because I'd like to get to the next unit for today. All right, so we got CS2. Each carbon gives you 4. Each sulfur gives you 6, and there are 2 of them. So we'll add those together. And you're going to notice real quick that this is going to look a lot like CO2, because when I draw my framework here, and I go like that, so there's my framework. That would be if I was doing CO2, right? Well, if I do CS2, not really much that's different other than just the letters that I put down, yeah? Even the number of electrons is the same. And then when I do their outer octets, I end up in the exact same situation. So there, I've used all 12 of my electrons. But now I have nothing to put on the central atom, so I have to start making multiple bonds. And you get the exact same structure that you did before. For CO2, anyway. And that's normal. And I could replace carbon with silicon, and you get the same thing. You could replace the sulfur with selenium, you get the same thing. As long as the number of valence electrons that you have to work with is the same, you get the same result. And so those molecules will look the same. And it turns out that that's true. All of these molecules in chemistry they're all identical. Because they all have the same number of valence electrons, which is kind of cool. All right. I'm going to hit clear. Boop. And now we can do it again for PCl3. So how many electrons does phosphorus give you? It's group 5, so it gives you 5. Or sorry, group 15, so it gives you 5. Each chlorine gives you 7 because it's in group 17. There are 3 of them. So I have 21 plus 5 is 26. There, we did that. All right, let's make our framework. So I'm going to go PCl, Cl, Cl. I'm just going to surround the central atom, make my 3 bonds. So that's -6. Boop, that's done. And then I'm going to put my electrons around the outer octets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Boop, that's done. Now we can do octets on the central atom. Well, I have 2 electrons left, so they're going to go right there. Boop. That one's done too. No need for multiple bonds. Everything is done. There's your structure. PCl3 looks like that. So you can do these real quick if you just set up all the rules and just go right down the list. So if you know the rules, you can do these molecules extremely proficiently. And that's the goal, is to get to the point where you can do these, where you don't even have to write down the rules anymore. You just sort of do them. All right, let's look at silicon tetrachloride here. So silicon is worth 4 because it's in group 14. Chlorine is still worth 7. We have 4 of them now. There's how many electrons I have to work with. So we're going to put silicon down. Oh, I didn't do that. There we go. There's my framework. That needed 8. Whoop, there you go. And then I'm just going to put electrons on the octets on the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Look at that. Boop, and we're all done. There you go, SiCl4. All right, we'll get rid of those two. Loop. We'll do formaldehyde. This is formaldehyde, by the way, CH2O. Each carbon is 4, each hydrogen is 1, there are 2 of them, each oxygen is 6. 12 electrons to work with. Even though I have multiple atoms, I'm going to do the exact same thing I did before. Just throw the carbon in the middle and throw the rest of them around the outside. So we did that. I'm going to go 2, 4, 6. Outer octets, I'm going to go 1, 2, 3, 4, 5, 6 were needed to do that. Boop. Central atom, I don't have an octet for carbon. I only have 6 electrons here. So I need to make multiple bonds. And there you go. That's the structure. Formaldehyde is just a carbon double bonded to an oxygen with 2 hydrogens sticking off of it. All right, we got C2F2. All right, each carbon is 4. There are 2 of them. Each fluorine is 7. There are 2 of those. I do that right? 14, 18, 20. Yeah, okay. What's the central atom? Well, carbon was listed first, so I'm going to do that. And I'm going to join them together. And I'm going to try and separate out the other things as symmetrically as I can. So I'm going to do something like this. So I needed 2, 4, 6 electrons to do those steps. We'll do the outer octet first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now we have 4 electrons for central atom octets. What I'm going to do is I'm just going to try and satisfy one of them. Now, you do have some options when you get to this point. And some of those options might be things like, well, wait, can't I just do this? Wouldn't that work? And yeah, technically everything would have an octet. But remember our guidelines from before where I said elements in group 17 want to form 1 bond, and elements in group 14 want to form 4 bonds, and so on and so forth? If you can ascribe to reach those guidelines, then you should. So while making this have a triple bond looks like it should work, then I have a fluorine making 3 bonds and a carbon over here only making 2 bonds. If there is a way for this carbon to make 4 bonds and this fluorine to stay only making 1 bond, that would be a better structure. And it turns out that there is. So if I take these 2 electrons and just throw them into this bond and do the same thing with the other pair of electrons so that I get this, now I have a structure that still satisfies the octet rule and also follows all those guidelines. And so this is the best structure. Notice how I'm using the word best structure. Yeah, there are multiple solutions for these, but there will always be one best structure. Now, as the molecules get more complex, what ends up happening is that it becomes more and more difficult to figure out what the best structure is. And at some point you get to a level where you can draw multiple structures and they're all equal, and there is no best structure. Or sometimes you draw a structure and then the rules don't follow what we observe in nature because there are other things at play there. What's important to realize about Lewis structures is that this is a model. And what we are doing when we do this is we're following a set of rules because we created these rules to get an answer that most of the time will match what we observe experimentally. This will not always work. And so if it seems like, wow, there are a ton of guidelines and rules and they sort of only apply most of the time, where are all these exceptions? Yeah, that's totally what's going on, and that's really unfortunate for learning. I'm going to try and give you simple molecules, but I do want to give you some of these down towards the bottom where you have to think about them for a little bit. All right, let's do C2H6. This one is significantly easier, thankfully. And so this is 14, it looks like. All right, I got C2. I'm going to put those in the middle, and I'm going to go H, 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 H. And I'm going to do my framework, so I'm going to do this really quickly. Okay, so the blue one I've already counted, so we're only going to count these other ones that I put in. 2, 4, 6, 8, 10, 12. Oh, I forgot to count this right here. So the blue one, I was all ready to impress you guys with like, oh, look, it's done. There we go. Now it's done. Whoop. We finished it at step 2. Sometimes that just works out. If you have all C's and H's, the molecules are super simple. And there's your Lewis structure. This is ethane. What do we use ethane for? I don't know. We use methane for natural gas. Ethane is used for something. Propane is used for barbecuing, and then butane is used for lighter fluid. But ethane is just kind of there. All right, last one. We got CNBR. That's what we get to work with. And I'm going to treat it the same way. C, and then the other ones are going to go around it. Boop, boop. So that was 4. Let's do outer octets. So 2, 4, 6, 8, 10, 12. All right. Well, now I have nothing for my central atom to bind to, so now I got to make multiple bonds. What do you pick? Well, again, we got to follow those guidelines, right? Group 7 only wants to make 1 bond, so if I can keep this one like this, we're in good shape. Group 5 wants to form 3 bonds. Well, that's good because I need 3 bonds so that my carbon can have an octet. This is the best structure. Now, if you try to put the bromine on the side with the nitrogen, you're going to end up with a real mess. You'll get something that looks more or less like this. But then now you're not following the guidelines, right? Nitrogen wants to make 3 bonds, but it has 4. Carbon wants to make 4 bonds, but it only has 3. The best structure is this one. And again, you can get that by just remembering the first atom listed is the central atom. So put it in the center. Don't make something else the central atom. All right. The online text and the worksheet should have lots of practice for these. Make sure that you do practice your Lewis structures because you're going to use these a lot in 161. And that's kind of the point of this class. So, all right. I believe that is it for this chapter. Hooray. I didn't unmute the music, though, so hold on. There you go. All right. The screen will go blank while I open up chapter 11. Give me just a second here. Why would you open to desktop? That's silly. Let's just do that. All right. Unit 10 was covalent compounds and just drawing structures. We discussed their properties very briefly. Now what we're going to do is we're going to take everything we've learned about various compounds and give them names. How do you name stuff in chemistry? Can I just read the letters one after another? Can this be HCN or ClOH or NaBrO4? Like, sure, you can say that, but that's not really how we name stuff. Like, nobody calls me WES, right? Everybody calls me Wes or Professor Wes or Mr. Hillman or whatever. We have to give names to these compounds so that we can print something that can be read in a language because we speak a language. If we were all really great at symbolic stuff, we wouldn't have to deal with half the stuff in this class because you would immediately understand it by looking at it, right? So some people get confused by symbols. And sometimes those people will be working with chemical compounds. In the nursing industry, for example, nurses are trained in a lot of like the biology of healthcare. Maybe not so much about like what the formula of something is and like what the formula does, because that's not their emphasis. They don't care that this is an oxidizer. They care that they can recognize this medication because that is what they administer, and then how much is the dose should be, and so on and so forth. So it's sort of a language issue that we give everything names, and so that's why we're doing this instead of just relying on symbols for everything. So what we're going to have to do first is we're going to have to categorize everything into a bunch of different categories so that we can name it. And what we're going to do from there is we're going to take what we've categorized into each of these three categories here, and we're going to apply unique rules. So there's going to be ionic rules, molecular rules, and acid rules. And which rules we apply depend on where we categorize. Okay, so this is going to seem like a really well duh sort of bit at the start, but I guarantee if you're the kind of student who just dives headfirst into the problem and then gets overwhelmed, if you don't categorize your compound into which set of rules you need, you're going to struggle in this section. And I don't want that. So make sure that you are carefully considering what your molecule is before you start anything in this chapter. And that's what this first section is about. How do we categorize our compounds? Well, we sort of already did that. There's covalent versus ionic. We've already done that. We're going to do it again, and then we're going to add one extra stipulation in for acids. What is nomenclature? Nomenclature is a systematic way of naming stuff. We're going to set out a very, very specific algorithm for naming everything, and if you break the algorithm, you get the wrong name. Follow the algorithm, and you'll be in great shape. So it's real important. Be meticulous. Don't skimp on the rules, and don't assume what the rules are. If you aren't sure, come back to the Unit 11 slides, because it's an online class, right? Go look up the rules. It's fine. I don't give a shit. You will eventually learn them as you do this enough times, right? And that's the goal. If you haven't learned it by the quiz, whatever, go look it up and then keep practicing it for the exam. And by 161, hopefully you will have learned it. That's my intent. Don't feel bad about looking at the rules, okay? Because you really have to get the rules right, or else everything in this section falls apart. So let's start here. What category does the thing I am looking at belong to? Because it's going to fall into one of these categories. Now, these first two are the same category. There's just a little bit of a gimmick involved that we'll mention when we get there. So this is the Ionic category. If something is ionic, it contains a metal or a non-metal. Now, it may also contain a polyatomic ion. This is the molecular or covalent category. You're going to see the words molecular and covalent used interchangeably in texts. And I find that super frustrating. Like, just stick to something, right? Covalent compounds form molecules, but for some reason, everybody likes to call things molecular compounds as opposed to ionic versus covalent, which would be really easy. So I apologize on behalf of all chemists everywhere. You'll just have to get used to that distinction. And then finally down here, we have another category of compounds called acids. Acids are something that we have not talked about. And nobody can see that color pen because even I can't see that. There we go. We already know the difference between ionic and molecular. How are acids different? Acids contain a special ion, and they're sort of the in-between between molecular and ionic compounds. They look like molecular compounds, but they still split apart into ions, one ion of which is called hydronium. H plus in a solution will often form hydronium, which is H plus and water mixing together. If a substance is intended to be interpreted as an acid, the formula will begin with H. Now, there are some exceptions, unfortunately, such as water. In fact, water is kind of a weird exception because water is the limit of what you can call something an acid. If you are a stronger acid than water, you are an acid. If you are a weaker acid than water, you are a base, it turns out. Water is the neutral midpoint. And so, even though it starts with an H in front of it, we don't describe it as an acid because it's technically neutral. That's a weird edge case. So there are some exceptions out there for things that fall very, very, very close to neutrality. But all the examples that I'm going to give you, with the exception of water, will be named like acids. So your first goal is just to look for, is it ionic, is it molecular, or is it an acid? And remember, there are easy ways to do that. Ionic compounds have metal or polyatomic ions. Covalent compounds have nonmetals. Acids start with H. That's really all you have to look for. So here are some examples. Let's categorize those for ourselves here. So this first one, it starts with H. It's an acid. The second one, no metals. They are all nonmetals. So this is covalent or molecular. And then the third one has a metal in it, so it must be ionic. Easy as that. All right. This seems like such a trivial first step. If you do this first step, it will save you so much agony in the naming stuff that we're going to go over on Tuesday. So I'm going to have you categorize these each as either ionic, covalent/molecular, or acid. Okay? Put one in the correct category, or put each in the correct category. We'll go over the answers, and then we'll be done for the day. See you in a few minutes. All right, one more minute. We'll go over the answers. Sorry, I'm answering endless emails. This is my life, apparently, during these breaks. All right, let's go over the answers. What am I emailing other faculty about? We're trying to figure out how to... We're thinking about renaming Chem 121 and 140 because we get too many students that are put in the wrong spot. And everyone loves my ideas. That's great. So I'm going to underline all of the metals. Remember when we did this last time? I'm going to do the same thing. So there's our metals. Here is an ion, and here's another ion. Here's another ion. So these are all ionic. There you go. That's easy now. And then the next thing that I usually go do is I go looking for H's. So here's an H, here's an H. So these must be acids. And then I only have one left, and he's kind of lonely here. So we'll make him fabulous in purple here. Oops. It's the wrong pen, though. Boop. So this is molecular. There you go. So if we were naming all of these, we would apply the same rules to each of these three things. And so we're going to do that first when we come back on Tuesday. This one for the molecular compound follows the molecular rules, which we're going to do second. And then finally, for acids here, we're going to do the acid rules third. So that's what we're going to be doing on Tuesday, tomorrow. We did finish Unit 10, so that means that a quiz is going up for Units 9 and 10. So that's going to be quiz number... I don't know what quiz number we're on. I don't know. Some quiz will be due Tuesday next week, which will be... Not Tuesday, I'm sorry, Monday next week. Which would be the 24th. All right. I will get the correct number for this next time. I don't know what number this is, so whatever, right? But there will be a quiz that will be due for Units 9 and 10 in a week, since we finished that. I want to thank everybody for coming out to the lecture. Let me know if you have any questions over email or the Discord. And have a wonderful rest of your evening. So I will see you tomorrow. Take care.